Hi, my name is Bill Fortney. I'm the director of NC State's Mechanical Engineering Systems BSE program. And you know, a lot of times people ask me, why is the systems perspective so important? And how is it different from traditional engineering design? Well, if you've got about 20 minutes, I would like to explain to you the systems perspective and hopefully give you some thinking that can help you in your design journey. Well, you don't need to see me when I'm talking, so what I'm going to do is switch screens, bring up some graphics to help to explain these things to you, and then I'll get on with answering the question. To answer that question, here's what I would like to do. First, I'm going to talk about analysis and traditional design, talk about the challenge of real-world problems, talk about systems and the systems perspective, then show how that's embedded into systems engineering and give an overview of that. Then, with that foundation, I want to show how systems engineering methods complement traditional design, how the two together enable us as engineers to effectively solve real-world problems. Okay, so one of the things that we do very well as engineers is analysis, or analytical thinking. In the analysis paradigm, when we want to understand something, we take it apart, we understand the parts, then we combine our knowledge of the parts into an understanding of the whole. That is the process, and it's the foundation of most of our engineering classes. It's how we as engineers solve complex problems. We break it down, we use models, free body diagrams, we apply our theory, and we solve the problem. And it works very well. I want to introduce right now a case study that I'm going to use several times through this explanation. So in the picture, you see the Marine Corps CH-53 heavy lift helicopter. In the back is a tail rotor, and inside of there is a tail rotor gearbox. So in one of our capstone design projects, the sponsor came to us and they said, okay, we have this gearbox. What we would like is for you to design a dolly to support it, to transport it, and to orient it. And they gave us some facts, like the gearbox is about 500 pounds, and different orientations that they wanted it to go. So for instance, in the orientation that you're looking straight on the page, it needed to go -25, and then all the way up to 90 degrees. And like good engineering students, our students studied the situation, understood what was really needed. We're going to talk a little bit more about that later. Then they performed conceptual design and came up with a solution the customer was very, very happy with. So then they took that conceptual design and they broke it into pieces. For each one of those pieces, they then studied it and performed detailed design in order to design every little piece. They used all of the strength analysis that they had studied, all of their mechanical engineering courses, to determine how large each beam needed to be. What's the torque going to be on this part? So what size does the bolt need to be? Worry about shear and bending and all of the detailed analysis pieces that they had been trained in how to do. And they came up with a design that was very successful and that the customer was happy with. They used analysis. Analysis is essential to us as engineers. It's what makes us engineers. It's what allows us to take a set of specifications, perform detailed engineering design, and come out the other side with a product. But if we're going to be effective problem solvers, we need more than just analytical thinking. Because when we go into the real world, our problems are not going to look like this. They're going to look like this. We're going to find our problems in the midst of a messy problem situation. A situation that has many, many different things pushing on it and making it messy. And in the midst of that situation, we're going to have a customer with a need. That customer is going to come to you as an engineer and want you to completely satisfy his need. That customer does not want you to design and create for them a widget. That customer wants you to satisfy their need. They want you to be able to go into that messy problem situation, understand what is really needed in order to solve their problem, represent that in terms of specifications or requirements, perform engineering design, and to deliver a product back into that messy situation that satisfies their original need. That's what we do as engineers. That's what the customer wants us to do. And in order to do that, we also need the systems perspective. Now, when I say systems perspective, what do I mean? Let me start with defining a system. So here's my very technical definition of a system. A system is a group of things interacting to achieve a common objective. So for example, a car, something we're very, very familiar with. And systems have some unique characteristics. First of all, systems are composed of parts, like a car, tire, steering wheel, lights, gas tank. I could go on and on. But typically when we talk about cars, we don't talk about parts like that. We talk about things like the fuel system, something that has many parts itself, each of which are composed of parts working together to perform a little function in that. Or the drive system, the safety system, suspension system, braking, electrical. You get the idea. So systems are composed of parts, but usually those parts are systems themselves. Okay, another characteristic. Each part plays a role in meeting the objective. And we can see that with a car. Each part has a role. So like for instance, the braking system. Its role is to slow the car down. That's its role in there. The drive system, its role is to speed the car up. So every component has a role that it plays in meeting the objective. Another characteristic, the parts interact in order to meet the objective. So for example, the safety system and the drive system, they interact. You go to try to start your car when it's in drive and it won't let you. Why not? Because the safety system and the drive system are interacting and they won't allow that to happen. Another perspective, part performance in meeting the objective is influenced by at least one other component, the drive system. The drive system cannot deliver the horsepower that it needs to unless the fuel system gives it the flow that it needs. Every part in a system, its performance is influenced by at least one other component. Okay, now there's one other characteristic about systems that we've ignored, and it's this word at the top, common objective. If you look in every one of the characteristics, you see that word objective. It influences everything about a system. So, what is the objective of this car? And we could sit here and talk for a long time, but we don't know. Because if this car was part of a military transport system, it would have one objective. If it was part of a family transport system, it would have another objective. If it was part of a NASCAR system, it would have another objective. As would the way the parts interact, the role of each part. The fuel system in a NASCAR system is very different than in a family transport system. So you see, without knowing that objective, it changes everything about a system. So one last characteristic is that systems are part of a wider system. That wider system defines their purpose, as well as the purpose of every single component within the system. So, in review, a system is a group of things interacting to achieve a common objective. That common objective is defined by its wider system. And that common objective defines the purpose of every single component within that system. So, just like with analysis had a way when it wanted to understand something, how it did it. Same with the systems perspective. So let's say we were designing a strut. It was our job to design a strut. The analytical approach says that the first step is to take it apart. The systems perspective says the first step is to identify the wider system. So our strut is part of a suspension system that's part of a military transport system. The analytic paradigm says the second step is to understand the parts. In the systems perspective, the second step is to understand the wider system. Understand the military transport system. Where's it going to be going? What kind of environment is it going to be doing? What does it need out of the car? Is the car carrying things that have to be held very, very, very still no matter what the road is? Understand that wider system. The analytic approach says then you take your understanding of the parts, assemble it into an understanding of the whole. The systems perspective says transfer your understanding of the whole into what is required for every part. So now, based upon what we know about this military transport system, what's required of our strut? We've got a military transport system that has to maintain very, very, very stability, even in very uneven roads. So it's going to have a feedback control system to keep it steady. Well, that means the strut's going to have to be able to have that ability to adjust at that sample rate and all the things that would go along with that. That's the systems perspective. So if you look at our case study, our students looked and saw that they were part of an aircraft repair system. If you can imagine a very, very large shop floor, you can see there's several helicopters in there. There was their helicopter. The gearbox comes off. It goes through some rebuild processes, and then it's put back on. When they looked at more detail into their wider system to understand it, they realized that there were many operations that happened before the rebuild shop. Like it had to be cleaned, it had to be painted. And then there were several operations after the rebuild shop before it was put back on. They took that understanding and they transferred it into what was required of their dolly that was going to be built for the rebuild shop. Okay, so this systems perspective that we're talking about is embedded into a field called systems engineering. So what is systems engineering? Systems engineering is a way to effectively engineer and create systems. And systems engineering gives us tools. It gives us a set of tools for actually designing large-scale integrated systems. It also gives us a set of tools for just managing what a large effort, most design efforts in large integrated systems really are. Now, we're going to come back and talk about some of the tools to help us design in just a minute. But systems engineering is represented in lots of ways. And here's one way. This is from the Department of Transportation. So basically what systems engineering does is it starts over on the left-hand side with a need. It understands the need that the customer has. It develops that need into a concept of a system that would satisfy that. It then develops it further into very, very specific systems requirements. It takes those systems requirements and embeds them into a high-level design, into subsystem design, all the way through to detail design until the entire system is designed in a way that satisfies all those requirements, which meets the need. Then as the system is being built, as every component is put together into subsystems, it's verified to make sure that the requirements that were originally defined, that it meets those. As it's built up more into more subsystems, those are verified. It continues to be built up until the entire system is built up. It's verified that all the requirements are met. Then finally, the system is validated to make sure that that original need that existed is truly met by the system. So that's systems engineering, and it's a very, very, very broad field. And I'm not trying to make you a systems engineer, but no matter what kind of engineer you are, if you will use the tools from this first part of systems engineering, it can make you much more effective at satisfying that need of the customer in that messy situation. So let me show you how that works. What systems engineering methods, those very beginning ones, do is help you take that messy problem situation and perform engineering design. Systems engineering gives you the ability to truly understand what needs to be designed and perform conceptual design. So you have a design that will meet the customer's needs in that messy situation. Traditional engineering design methods allows you to perform detailed design to actually realize a product that will go back and satisfy that customer's needs. So the two complement each other. They're a team and working together, whatever kind of engineering discipline you're in. And I mentioned those beginning tools in systems engineering. I'm not going to talk about these, but I just want to show them to you. These are the tools that systems engineering offers you that can help you in whatever engineering discipline you're in. So you can go and research those on your own and learn how to better do them. I'm just showing you the thinking right now. Okay, so let me show you how this complement works back with our case study. Traditional engineering design is what allowed our students to take this gearbox with all these loads, with all the orientations on it, and come up with a very elegant, complicated solution that satisfies the problem that the customers were very, very satisfied with. Systems engineering is what allowed them to look and say, okay, this 500-pound gearbox, as we look at the problem situation, as we look at the wider system, we realize that that cart's going to get pulled by a forklift. That there may be times it hits a pothole or it hits something and stops abruptly. The operator is going to stand on the cart and they're going to be working. They're going to be tightening things. So that 500-pound load is only part of the picture. There's actually more loads that this thing is going to be subjected to, and we have to now take those loads and use our traditional engineering and do the detailed design. So systems engineering effectively designed what needed to be designed. If any of those loads had been left off, then the detailed design wouldn't have been performed properly. The detailed design is what allowed them to take those loads, design a system that would hold up under those. Let me give you another example. If you'll notice in this design, the very, very center is completely open. Traditional engineering design is what allowed them to support a 500-pound gearbox rotated in multiple directions with the center completely open. An extremely hard design problem that they were able to solve with traditional engineering design. Systems engineering is what showed them the need for that. When they went and looked at their wider system, they realized that when that gearbox came off the helicopter, that it was put on a cart in a horizontal orientation like this. But several of the operations that it had to go through, like painting, required it to be in a vertical orientation, on a different cart. The only place that could change the orientation was the rebuild shop where they were working. And what would happen is it would come in one orientation, be taken off, put in the rebuild section, the orientation would be changed, then it would be put on another cart. So what they realized is that pretty picture that they had where parts just flowed through, it wasn't pretty at all. But the gearbox was always being taken to the rebuild shop, and every time it was being taken off, put on another device, the orientation changed, and put back on another cart. So what they realized is, when they studied that wider system, if they could design their device so that it could change the orientation, the gearbox could come off, that the back could be open so that it could be painted, it could be cleaned. If they could accommodate all those operations, then it could come off the helicopter, stay on their cart all the way through, and then go back on the helicopter. By doing that, they turned a cost-only project into a cost savings project because they eliminated all of those transfers. They eliminated all the times when the gearbox could get damaged, all the time in transferring it. So by seeing that right up front and identifying a design requirement that the back had to be open, they were able to then accommodate and turn that from a cost-only project into a cost savings. The complement between systems engineering, identifying what, and traditional engineering methods, then going through and doing the detailed design to actually design all of the pieces with that. So, what's the takeaway? Here's what I want you to go away with. When you design, the first thing I want you to do is to step back and understand the wider system your thing is a part of. Identify it, understand it, define exactly what you're trying to accomplish in it, and then transfer that understanding into requirements for your thing. The second thing I want you to do is to understand the other components in your system. You're not alone. Your thing is not alone. What do those other components want from you? And how does your thing influence and interact with those other components? And then perform your detailed design with that knowledge in mind. So if you will do these two things, I promise you that it will make you a better designer. Now, they're not easy. It takes a while to learn to develop this systems perspective. But if you do, it will allow you to reach into that messy problem situation, really understand what is needed, use your engineering skills to then deliver a system back that satisfies that customer's needs. It will make you an effective engineer. So thank you for listening, and good luck on your design journey.